Welcome to the deep dive. Today we're looking at something you can't see: deep underwater flooded members in subsea structures.
Yeah, and these aren't just small issues. We're talking about potential structural problems that could compromise, an entire rig or platform.
Absolutely critical.
Yeah.
So our mission today is to explore the tech designed to find these hidden floods. The Impact Subsea Flooded Member Detection System, the ISFMD.
Right, specifically how their Seaview V3 software makes it work. It's pretty neat how they use sound.
Sound waves giving us eyes underwater.
Yeah.
Let's dive in. Okay, so let's start with the basics. You're offshore, maybe on a vessel, needing to inspect this huge underwater structure. How does this software, Seaview V3, make that less complicated?
Well, the setup is actually designed to be really smooth. You install the software, maybe from a download, maybe a USB stick.
Okay.
And you get this screen. It's quite clean. Apps on the left, sensors it finds in the middle, COM ports on the right.
And finding the sensors, is that manual?
No, that's the clever bit. The first time you run it, Seaview V3, it automatically scans every communication port on the computer.
Every single one.
Yep, and it tries all the known baud rates, the data speeds. So if you've plugged in something like their ISFMD FMD probe, boom, it just finds it. You pop in a one-time license file, and the specific ISFMD application is just ready to go.
So for the user, that means less time pulling their hair out trying to get things connected.
Exactly. Less troubleshooting, more time actually doing the inspection. Offshore, that time is incredibly valuable.
Makes sense. That auto detect sounds like a huge relief. But all right, the core function, detecting the flood itself, how does it see inside a steel member deep underwater?
Yeah, that's where the acoustics come in. So on the main screen of the application, you actually see a live 3D model of the probe, the ISA 500.
Like a little digital twin.
Pretty much. It mirrors exactly how the ROV or the diver is holding and moving it. And visually, you see the probe graphic pushed up against the member you're testing. And there's this green acoustic beam shown going into the member. That represents the sound pulse it sends when you hit ping.
Right, the sound wave.
Precisely. Now, a really crucial step for the operator is entering the member's diameter correctly. Let's say it's 0.21 meters, 21 centimeters.
Why is that so important?
Because that tells the software where to listen for the return echo. It shows up as a blue box on the graphic. It defines the expected path length.
Gotcha, so it knows the distance to the back wall.
Exactly. If the sound pulse goes through, hits that back wall, and reflects back to the probe within that expected time or distance.
And there's water inside.
Bingo.
Yeah.
The software flags it as flooded. If there's no significant return echo detected in that window, it assumes it's full of air or gas and marks it dry.
Can you adjust things, like if the signal is weak?
Oh yeah. You can tweak the transmit power. And interestingly, if you think it might be filled with something else like oil or glycol, you can actually input the specific speed of sound for that substance to fine-tune the detection.
That's quite precise. So how critical is getting that acoustic measurement right? What are the real stakes if you get it wrong?
Oh, it's absolutely paramount. I mean, think about it. If you wrongly identify a member as flooded, you might trigger really expensive, unnecessary repair.
Right, wasted resources.
But potentially worse, if you miss a genuinely flooded member, well, that compromises the structure's integrity. It could eventually lead to a failure, which is, potentially catastrophic for the asset and safety.
So this isn't just about convenience, it's fundamental to making safe, informed decisions about these huge, expensive structures.
Definitely. You're replacing guesswork or assumptions with actual verifiable data. That's indispensable for maintenance planning, risk assessment, and just ensuring the thing stays standing safely.
Okay, so we have the detection,
Yeah.
but inspecting a whole platform involves checking potentially hundreds of members. How does this system handle that scale efficiently? It can't just be pinging one member at a time, setting it up from scratch each time, surely.
No, absolutely not. The workflow is built into it. So you can define individual test members in the software. Give each one a name or ID.
Okay.
You set its parameters, diameter, maybe adjust the transmit power needed. You can even put in its angle length and depth just for a better visual representation on screen.
And then you take the reading.
Yeah, you make sure the probe has good contact sometimes. The ROV needs to do a little spot cleaning first. Then you hit ping, get the result. Then you click add reading.
And that logs everything.
It logs the flooded or dry status, but also where on the member you took the reading. You can specify, say, 2 meters along the member at the 45-degree position around its circumference, Really precise documentation.
That level of detail must be vital.
It is, but the real time saver for big projects is the pre-configuration. Before the vessel even leaves the harbor, you can create a whole list of all the members you plan to inspect.
So you upload a plan, essentially.
Yeah. Exactly. Add all the members, their names, diameters, locations, everything. Save that configuration file. Once you're offshore, you just load that file. All the members are there, ready to be tested.
That must save a massive amount of time compared to setting up each one individually out at sea.
Huge amounts. Vessel time is incredibly expensive. So streamlining that data entry and setup is a major win.
Then, once all the tests are done,
There's a report.
Yep, you click Generate Report, and it creates this comprehensive HTML file, lists every single member tested, all its configuration settings, and every single reading taken, including the location data.
So full traceability.
Complete traceability.
Right.
Makes auditing, reporting back to clients, and long-term monitoring much, much simpler.
It really sounds like a powerful system. Taking something complex like acoustic inspection and making it, well, manageable and visual. From the smart setup to the 3D guidance, the precise detection, and then that comprehensive report. It's quite the aha moment for underwater integrity checks. It really is. It elegantly solves a hidden problem. And, as you think about this technology, using sound to find hidden water deep beneath the waves, it does make you wonder, doesn't it?
How so?
Well, what other invisible challenges are out there in all sorts of fields that we could potentially solve just by applying existing technologies like acoustics in new and clever ways?